Homework Hotline, what is your emergency?
Hey there, how are you guys doing? I hope you are ready to have your minds expanded a bit.
To see the possibilities that you can achieve.
To understand that you have abilities far beyond what you imagined.
We are the Homework Hotline. We are here live every Tuesday and Wednesday to help you with your homework problems.
All three of us are teachers, so every school day we help students just like you. That's what we do. So give us a call here at 720-424-1666. Because when you call in, we can help you a little bit more in depth, and you can watch us while we answer your question. We can also ask you clarifying questions if we don't understand what you're asking.
So you can watch our show in many, many different ways. For live broadcasts, you can watch us on Comcast Channel 22, Prism TV Channel 8007, livestream.com. You can search for DPST 22. You can get us at Facebook Live at EG Homework, or you could watch us on YouTube at Denver DPS TV.
So I'm Sam. I teach science at the Contemporary Learning Academy, and over here next to me we have Nathan and Becca. They both teach math at Emily Griffith High School. Both of our schools sponsor the show.
And today we're also going to have a science demonstration with Sam. I hear there's a lot of pressure in this one.
It's definitely not something that we can just wing. You'll need to keep watching to find out more.
So that we prefer that you call us. We understand that you also like to use social media. We actually have Jeff here monitoring our social media for your questions.
That's right. Yeah, I'm monitoring social media today, and we've got a bunch of questions lined up today. And we also have a very important trivia question that we're going to be talking about today as well. And so it's going to be exciting. And I'll give you the trivia question right now, okay? And it is, what is the hardest substance in the human body? What is the hardest substance in the human body? That is the trivia question. So if you know it, call in, let us know, and you could win a prize, right? Yeah.
All right, well, since Jeff mentioned that you can send in your questions to us and he would field them to us, let's give you that contact information so that you can get a hold of us if you have an answer to the trivia question or if you have a homework question that you want some help on. So our contact information, you did get maybe the phone number earlier. It's above me. It's on your screen. That'll be there the whole show. But you can get in contact with us on social media. If you go search for us on Facebook or Twitter at EG Homework, you could text your answers to your questions your questions to us at 970-680-3771, or you could email those questions or trivia question answer to us at homework@emilygriffith.edu. So let's go back to Jeff and see if we have any questions that need to be answered.
All right, yeah, let's hop to the board, shall we? And we have a math word problem. Actually, this is interesting, and this is about. If I can click on that bad boy there. Okay, yeah. So now this is a kind of a fitness kind of question. We know a lot of you out there like to run, jog, and be healthy. So this one says, Maria ran 7.5 miles on Monday. On Wednesday, she ran 4/5 the distance that she ran on Monday. And on Saturday, she ran 1.5 times the distance she ran on Wednesday. If Monday, Wednesday, and Saturday were the only days Maria ran, what was the total distance that she ran during the week?
Woo!
Yeah, I know, it's complicated.
Oh my gosh. Well, I guess I'll answer that one, and then also, as I answer it, I'll give you guys some strategies to deal with massive word problems like this, because those can be very intimidating. So I'm going to almost think out loud with this one while I work through it, just so you can kind of see maybe the process of thinking with that. So if you cut to my screen, I've actually copied the problem and I put it on my screen. One thing we know, okay, so Maria, she ran 7.5 miles Monday. So I'm actually one of the things that I do when I solve word problems or work through word problems is that I'll make a little list to the side of all the information that I know, all of the givens, just because I don't like to have to go back to my word problem and reread the whole thing and sift through it all over again. So on Monday, I'm going to write this down. So Monday was 7.5 miles she ran. And then it says on Wednesday, so this is my next fact here. On Wednesday, she ran 4/5 of the distance she ran on Monday. So I'm actually going to stop there. Even though the sentence doesn't stop there, it does say and, but I'm going to stop there and record the information that I have. I'm going to say, all right, Wednesday, she did 4/5 of what she did on Monday. And what she did on Monday was 7.5 miles. So we'll say 4/5 of 7.5 miles. So there will probably be some calculating with that, but we'll deal with it later if we need to. And then it says also on Saturday, she ran 1.5 times the distance she ran Wednesday. So on Saturday, she did 1.5 times Wednesday. So actually, I'm going to just even write Wednesday. I'm going to write that there. Wednesday. And then it says, if Monday, Wednesday, and Saturday were the only days she ran, what is the total distance? So I need to, when I'm finding total distance, I need to add everything up. All of these distances up, I need to. So for me to be able to find what she did on Saturday, I might also need to figure out what she did Wednesday. So let's kind of work through this. So again, Monday, she did 7.5 miles. And we're going to add that to 4/5 of 7.5 miles. So 4/5, any fraction of something. That word of, keyword, meaning we need to multiply things. So we're going to be doing plus 4/5 times 7.5. And then I also need to add 1.5 times what we did on Wednesday. So it'd be 1.5 times what we did on Wednesday. And I'm going to highlight that here. This is Wednesday. So maybe I'll color code this. Here's Wednesday. And then, so we need to do 1.5 times that. So we'll do 4/5 times 7.5. So now we've got our expression that if we were to simplify all of this and put all this together, then we would actually have what we're working with. Couple strategies. We could continue working with fractions, and that may be the purpose of this problem. But personally, I don't love working with fractions. And me looking at these fractions right here, actually decimals might be a little bit easier to do this. So I'm going to change this 7.5 to 7.5 plus, and then 4/5 as a decimal. If we think about how many tenths that is, we could get it into a decimal. So using just equivalent fractions here, we could multiply numerator denominator by the same thing, and we get 8/10, which is actually the same thing as 0.8 place value times 7.5 plus 1.5, and then times again 0.8 times 7.5. So I just rewrote my whole expression right there with decimals instead of fractions, because they may be easier to work with. This is not the only way to do this problem, of course, as with a lot in math, but this is one of them. So from here, we need to simplify it. So to simplify, we need to do our order of operations, which we had one of these the other day. So we're going to start with our parentheses. So 0.8 times 7.5, we get 6. So that's actually the distance she ran on Wednesday, is 6 miles. So we have 7.5 plus 6 miles plus 1.5 times that 6 miles. So we did our parentheses, no exponents here. We're going to go to multiplication or division. We do have some multiplication here. That it was that one, excuse me, oh, where that came from. It was that 1.5 times the 6. So that would give us 9 if we multiplied those together. And that is what she ran on Saturday. So adding up our Monday, Wednesday, and Saturday, we get all together 22.5. So she ran almost a marathon, 22.5 miles all week. She is quite a runner. So that again is just one, and let me back up to, let's see, here is our multiple choice. It was answer B. Answer B was our 22.5. So there you have it.
Yeah, I like that organization. I think just taking a second in the beginning and rewriting that important information, thinking about what you're looking for, because a lot of times I think students want to skip that, thinking like, oh, I'll save so much time, I'll just start the problem.
Right.
And they end up reading that problem like probably 4 or 5 times, trying to pull out information, and then still missing things because it's not really that organized. And
Or they miss something that was written in there.
Or they answer the wrong question, really, like a question that's not really being asked. So
Right.
the organization, I think, is really helpful.
It was the key. Honestly, it was the key for me. Word problems intimidated me. I was not into
Yeah.
math. I just whatever. But once I learned how to do that and pull out information and then not even look at the word problem anymore, you might have noticed that I didn't go back to it at all. I mean, I could at the end to check it, but yeah, pulling out that information and not having so much to deal with makes things a lot less intimidating.
Yeah, I agree.
So, all right, Jeff, we have any more questions waiting for us?
We do. We have many, many, many questions. And
Many
that's cool
questions.
what you said about the math problems, because I always ran into that problem in school. I'd be like, what? I didn't know anything about it. But anyway, yeah, we have a science question here, and this has to do with something that you might have heard of in maybe some like science fiction. You know, you hear of acid rain. Acid rain, and what is that exactly? Well, this is a question about acid rain for our science, and it says, we studied the water cycle in class and found that rain comes from water vapor in the air that collects and falls. But then I heard about acid rain. What is that, and where does it come from?
Yeah, so I mean, an acid rain definitely sounds really scary. It's one of those things that exists. There are instances of it being really scary, like in places where there's lots of pollution from factories. You can get pretty intense acid rain, something that could actually affect a person. But in general, and we've talked on this show about what an acid is versus a base, and some acid rain might be very lightly acidic, and we might only notice that it's acidic because of some minor effects. So I'll talk a little bit about what acid rain is, how it comes to exist, and then sort of some of the effects that we can expect. So just like the question mentioned, during the water cycle, or sort of in the course of water cycling through the planet, one of the stages that water takes is its water vapor in the air. And during that time, it's very possible and very common for the water vapor to mix with gas molecules that are floating in our atmosphere. So gas molecules that are floating in our atmosphere are things like oxygen and nitrogen. If oxygen or nitrogen mix with water, you're just going to get essentially air bubbles inside the water that have no real effect. Neither oxygen nor nitrogen in its atmospheric form are going to make water acidic or basic. They should allow it to stay neutral. But this other gas, carbon dioxide, which is one that we talk about a lot now, carbon dioxide is not a super common gas. 79%, I think it is, of our atmosphere is nitrogen gas. I might be a little off on that figure, but it's high 70s. 20-something% is oxygen. And then we have these little, it's like 1% or maybe a little more is carbon dioxide and water vapor. Anyways, carbon dioxide, CO2, when it mixes with water, you actually do turn that fluid, that water, acidic. And we see this in everyday life. I really love soda water, fizzy water. It's one of my favorite things. Sparkling water, I guess it's called. And that is literally just water that CO2 gas has been forced into. to make the bubbles that we all kind of know, but there's also sort of a sharpness to sparkling water, and that has to do with the fact that CO2 gas, when it's dissolved in water, makes that water slightly acidic. So there are instances of rain becoming acidic from CO2. I mean, that happens all the time, and so rain is probably commonly very slightly acidic. We wouldn't really call that acid rain, though. Typical acid rain is going to be water that mixes with a gas called hydrogen sulfide gas, H2S. And hydrogen sulfide gas can, in water, take the form H2SO4. It can combine with oxygen in the atmosphere. And if you get H2SO4, H2SO4 is sulfuric acid. And CO2 in water makes carbonic acid. Carbonic acid, even at high concentrations, is weaker than sulfuric acid. Sulfuric acid is a more aggressive type of acid. And there are a lot of, especially stories from like the 60s and 70s, when a lot of energy in the United States was produced from burning coal in an unclean way. One of the byproducts of that burning is hydrogen sulfide gas, and so you get gas emissions from the coal, and those emissions, the H2S specifically, mix with water vapor and create acid rain, which can potentially, harm your skin as it lands on it. One of the places we more commonly see, and if you want to see the effects of acid rain, go to a graveyard. I know that probably sounds creepy, but go to a graveyard, because graveyards are filled with gravestones, and gravestones are made of all different types of materials. And what you'll see is that most gravestones are made of things like granite and marble. Well, I guess mostly granite, let's say. But as you move around a cemetery, you can usually find older graves that are made of marble and limestone. Marble and limestone, due to their chemical composition, react with acids and actually break down. And so what you'll see if you go to graveyards, and especially look at these older graves made of limestone or marble, is you'll see pockmarks in the rock, and that's literally from rainwater dissolving out little pockets. You can see this in nature too. If you find a landscape that's covered in limestone, you should expect to find some areas that are pockmarked. Or if you find a rock that looks like it was pockmarked and dissolved away by rain a little bit, you can make a fairly safe assumption that it's probably limestone or some related rock. So anyways, acid rain is, as we think about it, as a danger to humans and the environment, is typically the byproduct of pollution. And the polluted gases mixing with water vapor to create a strong acid rain. But of course, all water on the Earth ends up becoming slightly acidic when it comes into contact with certain gases. So just to point that out.
So it's not like on this, like if, I don't know, like you have those movies like a Sharknado or something like that.
Right.
Like if the acid rain came down, it wouldn't melt your skin or anything.
No,
like
I mean, no. I think that in China they do still deal with this in some local areas. And what we're talking about is it's not good for you. It could be something where it might burn, maybe even more likely, you just get a rash or a reaction and don't even really know
Where it's from.
why. Yeah, it's not as
Yeah.
though the rain's going to fall and like burn a hole through your arm like cartoon style.
Yeah, right. Yeah.
You can make acid that strong. It just doesn't really occur naturally.
Okay.
Right, now every time I get a rash, I'm going to think it's the
Acid
acid
rain.
rain.
It's acid rain and those frequent trips to Beijing, right?
Yeah, right.
Excuse me.
All right, cool. Well, thanks for answering the question.
Oh, you're welcome. That's my job.
Well, let's see. Let's go back over here. How about another math question? Does that sound good?
good.
We have a
Sounds
math
fair.
question that has to do with exterior angles. And this one says, the measure of each exterior angle of a regular polygon is 45 degrees. How many sides does the polygon have?
Sounds like geometry. Is that right?
Yeah.
Yeah.
Yeah,
So
sounds like some geometry.
That's fair. I think,
All right.
I think you can
So
take it.
I'm going to write down one quick thing here. You said the measure of each exterior angle. So I'm going to just write each
is 45 degrees.
exterior angle is 45 degrees. And you said, what are we trying to figure out?
We want to know how many sides does the polygon have?
How many, spelled many wrong. How many sides? Okay. So, and we said a regular polygon. I'm going to write that down here because that's really important. Without this word regular, we would not be able to figure this out at all. So let's talk first about what a regular polygon is, and then we'll talk about what an exterior angle is and how we can use the relationship in exterior angles for figuring out how many sides this figure has. So the polygon is really any closed figure. So made up of straight lines, right, where the ends of the lines connect to form some closed figure, and there's no overlapping or anything here. This is a polygon. This is really any kind of shape, right? So I could, like, this would be a polygon. It looks weird, but that's a polygon, right? Because it's just made up of these lines that form this closed figure. So when we talk about specifically a regular polygon, we're talking about a polygon, like let's talk about like a square is a regular polygon. And if you think about what you know about a square, well, you know in a square, all the sides are the same length, and this is just notation, if you're not familiar, in geometry that says that all the sides are the exact same length. So what that means is if this side is like 10 centimeters, that every side is 10 centimeters. And then we also talk about, when we talk about regular, because right now we have an equilateral polygon, when we talk about a regular polygon, it also means that the angles are all the exact same measurement. So in a square, we know that they're all 90 degrees, but that they're all the exact same. So that's one thing about a regular polygon. Now, when we talk about exterior angles, what we're talking about is the angles on the outside. So these are interior angles because they're on the inside of the figure. An exterior angle could look something like, if I extended this line from this square, this would be an exterior angle right here. I'll just highlight it in blue. That's an exterior angle. So when we have a regular polygon or any kind of polygon, we have a bunch of these, right? Like I can actually keep going and say that I have 4 exterior angles. So what we're trying to figure out is, what if we knew that one of the exterior angles had a measurement of 45 degrees? So let's imagine that this was like, instead of 90, that this was 45 degrees. Now, when we talk about regular, we know all the interior angles are the same, so we should know that all the exterior angles are the same. So, because of this relationship. So, in this case, so it doesn't make it confusing, if I have a 90-degree angle out here, and this is a regular polygon, this would be 90 degrees, because this guy is 90 degrees, we'd have to have a 90-degree angle here, and everything around would be 90 degrees. Now, what you'll notice is when I add up all these exterior angles, 90 plus 90 plus 90 plus 90, you're going to get 360. And so there's something really interesting about regular polygons and their exterior angles, or any polygon and their exterior angles, in that what you're going to see is they always add up to 360 degrees. So if you're learning about this, you probably learned that the interior angles of a polygon are going to change based on the size of your figure. So like if I did I'm going to try to draw this freehand, see how this goes. Like let's say I did a polygon or a pentagon, and this is regular. You actually have to increase the angles to make up for the number of sides. So in a square, these are going to all add up to 360 degrees inside. In a pentagon, they're going to all add up to 540 degrees. So the first intuitive thought would be that the exterior angles should add up to something bigger, but it's kind of interesting because they always add up to the exact same number. And I'm going to show you a quick GIF that I think helps with that. Oh, I was looking at some voting stuff. Sorry about that. All right. So if we look at this image, what we have is, oh, where'd it go? Maybe I shouldn't have clicked on it. Okay, it's gone now. Okay, if you look at this image, what you see is you have 3 regular polygons, and if you were to shrink them down and make them smaller and smaller and smaller, you'll notice that they're always going to form 360 degrees. If you notice in the middle, there's a circle, and a circle is 360 degrees. So no matter how big, you could have like a 1,000-sided polygon, that's a regular polygon, If you shrunk it all the way down, they're all going to add up to 360 degrees. And another way to think about that is like, if we're making these angles on the inside all bigger to accommodate, then what we have to do is, that didn't work, we have to make these outside angles smaller to accommodate that. So it kind of works itself out. You notice like these were 90 degrees here. These look smaller than 90 degrees, right, to make up for that bigger size that has to happen inside. So on to the question. That's just a lot of vocabulary stuff and just some properties of regular polygons. The question is asking us, if each exterior angle is 45 degrees, how many sides do you have? So what we could say is, we're doing it really is we're saying, okay, I got 360 degrees. If I divide that by 45, we're going to say, like, how are you evenly splitting all of these exterior angles? So 360 divided by 45 is going to equal, I can never find where my pen is, 8 sides. So what you're going to have is a regular polygon where every exterior angle is 45 degrees, you're going to have an 8-sided figure or an octagon. So again, with a 4-sided figure, every exterior angle was 90 degrees, and they all add up to 360. If I have an 8-sided figure, they still all add up to 360. The angles just get a lot smaller. So
I liked that
helps.
GIF.
It's really helpful.
I liked that. I was picturing, I'm like, how's he going to explain that it's just kind of like a circle?
Yeah, without just being like,
right.
oh, every time, just trust me.
It just
adds up.
is.
Like you just actually see it.
Trust me.
Yeah.
Yeah, a lot of times when you move the geometry, it makes it make a lot of sense.
Yeah, it really does.
Yeah.
Yeah.
All right, well, we're going to take a break, and when we come back, we are going to have our science experiment. Woohoo! So see you soon.
Dental field is something that I really enjoyed since I was very little. I was very interested in teeth in general. I always wanted to be a dentist because my dad was a dentist back in Russia. So that was really, really interesting to me. So I decided to choose something, that would be in the same field, but I would get my certificate faster and I would be able to find a job and then continue my education. My name is Medina Tambieva and I'm a graduate of dental assisting program at Emil Griffith. Здравствуйте, я Медина Тамбиева. Я ассистент стоматолога и получила это образование в Эмиле Гриффит. I applied for financial aid and I got the full amount, and also I received a scholarship. And they paid for my uniform, my books, also amount of tuition that was left. I wouldn't be able to take this course without the scholarship because I didn't have money. My parents weren't working. I was the only one who had to support the family. Dental assisting course was online and I only had to come to campus once in a week. So that was really, really convenient for me. You have to really work hard for your dreams and your goals because it was really hard for me to come here to the United States. I had to be separated from my mom and my 2 brothers for almost 3 years. And it was really hard. I don't know how I did that. I was only 15. I think education is one of the most important things in your life. You have to think of what makes you happy, but also you have to be helpful to the whole community. Becoming a dentist is my biggest goal and dream in life, and Emily Griffith was my biggest step towards it. And I'm really happy that I'm a dental assistant now and I can move forward and work for my dream.
Okay, guys, well, welcome back to the Science Lab. Today we're going to be talking a little bit about just how airfoils work, and we're going to talk about it in the most basic sense to sort of think about how airplanes lift themselves into the air. This is kind of coming out of nowhere. I don't think it's really related to other science experiments we've done, but I do think that it's something that a lot of people have misconceptions about. How is it that planes really lift?
Because they're so heavy.
Yes, so much tonnage of weight.
If I understand correctly, I believe it's magic. I think we talked about this before.
It is magic.
Right,
Magic.
absolutely. So magic is the right way to fly. If you're out of magic, you can use lift.
Oh.
So let's talk today. We're going to talk today a little bit about lift and what it is and air pressure. So what I have for each of my participants here is a piece of paper. This is just scrap paper from my classroom. So it has physics stuff on it, but don't worry about that. That's not relevant. This can be any piece of paper. And a straw. For a second piece, we're just using empty soda cans, and we'll get to that in just a minute. But guys, if I get each of you pick up your straw. Okay, and go ahead and just stick it in your mouth because you're going to be using it to blow on stuff throughout here. Okay. So
Does it matter which side?
No, it doesn't really matter which side. Okay, and then what I'm going to have you do is I'm going to have you pick up a model with Nate's here. I'm going to have you pick this up, and let's just start by, if you guys would just blow directly on to the paper like that, and we'll just see what happens. Yes, very nice. Excellent technique, all of you. Okay, so what's happening?
It's lifting up.
Okay,
Yeah.
sure, it's lifting up, definitely. Why?
The air that you're blowing.
Okay.
The air pressure underneath it is more than the air pressure above
Yeah,
it.
so to get a little
Oh.
bit more sciencey, so a lot of times what we'll say is, okay, air is just blowing, and that's what's pushing it, and that's true. But thinking about it from a little bit more of a sciencey perspective, what we want to talk about is the idea that all the air coming at one side is creating air pressure on this side of the paper greater than on this side, so the paper starts to push away. It's really the differential in air pressure, right? If on the back side of the paper there was equal pressure pushing back, then the paper would move.
That's interesting. I never thought about it that way. I was just like, air is pushing on it, so it's going to move.
And that's what we typically do,
Yeah.
right? And so there's another thing we can do here that's even cooler. Well, that wasn't cool at all. But there's a cool thing that we can do. So this is what I'm going to have you guys do. And this sometimes works better if you just blow with your mouth, but I'm going to have you start with the straw. The straw is really for the next piece. Let's try with the straw, and if not, you can do it with your mouth. Let me give you directions, and then I'll have you do it, okay? What I'm going to have you do is I'm going to have you bring the paper up to your mouth or to the end of your straw, okay? And then you're going to blow over the top of the paper. And in fact, you can blow kind of right down onto the paper itself. Does that make sense what I'm asking?
I think so.
Okay, let's try it and see what happens.
So we're kind of just holding it like this.
Uh-huh. And yeah, and blow down hard on the paper. And
Oh, it's
maybe
kinda
down
lifting.
and across it. Oh, Nate
Oh,
just got a good
lifted.
one there. Nate, can you do that again? Okay, so see if you guys can do that. You're going down on top of it. There, Becca got it. Jeff got it. Keep blowing, guys.
Getting a little lightheaded.
Okay, let's just stop for a minute. So just a minute
Okay.
ago, you blew on a side of the paper and it pushed away from you. Now you're blowing on a side of a paper and it's coming in that direction. In fact, should be a little bit counterintuitive, right? Because I'm blowing on one side of the paper, and yet that is the side that is raising itself.
Yeah,
Why?
I thought it would push it down further.
That's what you would expect, right? So what is going on?
Something about the air pressure.
It's got something to do with that for sure. We're
well,
gonna figure
if
out
the
what it
air
is.
pressure,
So if we're blowing on it,
Maybe
it's
the
higher
pressure-
pressure, right?
Okay, so if it was higher pressure on top, it would push down.
Down.
So what does that tell us about where the pressure must be higher?
Below.
Down below.
Below.
Yeah.
but why?
But why is the question? Okay, and this is then, and there's a little trick here, a small piece of understanding about how air works and air pressure, and this little understanding I think explains the way a lot of fluids work. So, when air or any fluid moves faster than other air, okay, so we have two sets of air, and one side of the air is moving faster than the other, it will have lower pressure. Faster moving air has lower pressure than slower moving air.
Is that something to do with like the molecules or something inside, like moving more rapidly, being more spread out?
In a
little
way,
bit?
exactly, right? I mean, in a sense, over a given amount of time, you have a less total mass on that side. And if we could jump to my computer screen just really fast, there's a really simple graphic of this that we can sort of see. So what's shown in this, as soon as we get it up, is a side view of an airplane wing, something we call an airfoil. And we may do future experiments where we'll actually look at different airfoil shapes, but we're just thinking very generally today. So an airfoil is the shape of a wing, or a blade, a fan blade, let's say, that allows air to pass over differently on one side than on the other. So you guys can probably see from the graphic, we've got faster moving air on top of the wing and slower moving air on the bottom. And that has to do with the fact that the shape is different top to bottom.
It's allowing the air to go up, and it's kind of blocking the air from going.
Yeah, so think
on
about it
the
like this.
bottom of it?
The air on the top has to travel the same distance, it's going to end up at the end at the same time as the air on the bottom, but it has to travel a greater distance.
Oh.
So it has
make
to
sense?
make up for that.
So it has to
going
make up for
faster. Okay.
Right. So it's moving at a faster speed, and as we just talked about, that's going to create a lower pressure. And on a small scale, like blowing onto a piece of paper, you can get a piece of paper to lift. But on a large scale, when you get a really well-made airfoil and a lot of speed, you can lift many, many tons into the air. It's pretty incredible, huh?
Yeah, it is.
Wow.
Cool. All right, well, let's try one other little experiment. This one is really fun. Now, we can do this a couple times, but every time we do it, we're going to lose
That's my
the
straw.
cans that we use. This is a cool experiment you can do with just 2 empty soda cans of any kind. Doesn't matter the brand. And what we're going to do is again kind of try to tackle that counterintuitive idea that when I blow on something, it pushes it away, right? Because that's a typical idea that I think a lot of us operate under. So what we're going to do is I'm going to have Becca do this first.
Oh no, my straw.
Ew, I did too.
This be like Nate's always next to me, so I give him the opportunity to do a lot of stuff.
Which I like.
Spread out a little bit. So we're gonna make these fairly close together, and I'll see if I can get them set up for the side camera. I don't know if it's something we can do, but what you're gonna do, Becca, for us is blow between the 2 of them really hard using your straw. Okay, so if I could just let Nate, can I see your straw? So essentially, you're coming like right here, and you're gonna blow really hard between them. Does that make sense?
Yes.
Now before you do it, Jeff, what do you expect to happen?
Well, I'm thinking that they're probably going to go
Right.
like a side.
Absolutely. Okay, let's do it, Becca. Super hard,
I
Becca.
could blow harder.
You might have to come up a little bit, yeah, and right in the middle. Oh, didn't quite get it.
Let's try that again.
Try again.
Okay. They came together.
Did you see that?
Yeah.
Yeah,
Kind of rotated in.
Let's see if we can get somebody. Let's let Jeff. Let's let you.
Okay.
In. Okay.
So we.
You gotta really come close to it. Get your straw between them and blow hard. Came together. Okay, Nate, explain why.
Air pressure.
Air pressure, definitely. Well, so where must the
Okay.
pressure be lower? Let's just start with
So
that.
the pressure, if you're blowing here,
Yep.
like the air is going in between, the lower pressure would be here, right? Oh wait, sorry. The higher pressure would be
On the outside.
here
Why?
because it's not moving as fast.
Exactly. So when Becca or Jeff were throwing air through the center of these, you guys were creating a fast-moving patch of air. And as we just talked about, fast-moving air has lower pressure. So all of a sudden, all the air around the cans became much higher pressure than the stuff in between, pushing them together. If you do this, I've seen it done I've done it a number of times where if you really blow hard, they will bang into each other and kind of ricochet apart.
Can you
Which
do
is
it?
sort of neat. We can try. Let's see if Nate can get one for us.
Isn't it?
All right.
Isn't it true that airplanes are made out of aluminum too? Is that true?
Yeah, some parts of airplanes are made out of aluminum,
does that make
definitely, and extremely high-grade aluminum. So aluminum is a general term. We mix lots of things with the element aluminum to get different grades of it, different strengths,
And different
lightnesses.
weights, yeah.
Exactly. I use really lightweight stuff for camping, but it breaks fairly easily.
Right.
Airplane stuff is going to be real tough. And in many cases, I think they also are using titanium
Oh,
on
okay.
airplanes. Okay.
Interesting.
So, Nate, go ahead. Give us a whirl.
So am I actually putting the straw in between, or
Yeah, I mean, right up to that point, because you want to create that,
Okay.
that patch of air there, and really, come on, Nate, all the you know,
All
lung
the stuff.
capacity I
All
know
right.
you've got. Math teachers are famous for. Oh yeah. Let's. There we go.
is that better?
Oh, that looks beautiful.
All right. Is that close enough?
Yeah, I think that should be close enough. Let's give it a try. Yeah. essentially what we were going for.
They kind
did
of slammed
kinda
off of each
slow
other.
in.
Yeah, they
and
kind of slam off, and I think it's just cool because again, it just gets back to that idea.
Yeah.
And Jeff, I think, voiced it perfectly. When you blow air between two things, you would expect them to go apart from each other. And in some instances, we do see that, especially if you were blowing at one of the cans, you would push it away because
So
you'd
the air wasn't going like exactly in between the two cans. I think that's what happened
what's
the
happening
first
for
time
all of
I
them, yeah.
did
Exactly.
it. Was I kind of my aim wasn't so good.
Well, and the aim is
So-
really important, right? Because if you're blowing air directly at the can,
gonna
you're
blow
actually
away.
creating a high pressure space right there. It's when air moves laterally past something that it creates a low pressure space. So that sort of direct perpendicular air motion is going to put the pressure right onto the can, and then of course that pressure is higher than what's behind it, and the can moves away from you.
So, what we're seeing is like this rotation. It almost looks like, and I think that's maybe because of it's
Probably the
not
way
quite
we're blowing.
even, right?
Exactly.
So if theoretically, like these cans we like set this up really precisely
Yep.
and blew exactly in the middle, would we see them hit like that, or would
Yep.
they maybe come forward a little bit?
They should hit
They should just slam inside.
just like that. I mean,
Okay.
maybe a little bit forward because there might be patches of. Oh no, excuse me. They might even move a little bit backwards because there'd be patches of low pressure air here.
Oh, right, because the air is moving faster. That'd be interesting.
It would be, there'd be different ways that we could try to set this up, but I think that this sort of gets to the idea of the cool thing about these kinds of experiments, and there is not a cheaper experiment or easier experiment in the world you can do than blowing over the top of a piece of paper. And it's simple, I guess, but it's pretty amazing that happens. And it's a minor way to look at how this sort of really big concept of air pressure affects us in our lives. And you can do this in lots of different ways. You can take different materials that might be around your house and try to do this. Try to create different air pressure spaces and see how things move.
So it's the slower the air, the higher the pressure, and the faster the air, the lower the pressure.
That is exactly right.
Okay.
Which is probably something that gets mixed up a lot, right? I
So
would think
mixed up.
faster air, higher pressure is what I
Well,
would think.
and just like we talked about, the fact that the sort of direction of the air can create pressure space here versus it's not
Right.
so clear to us when we're going through our everyday lives, so it seems a little counterintuitive. But essentially, that's the basic concept. Faster moving air is lower pressure, slower moving air is higher pressure. And if you see out there in the world as you're going around, if you see things kind of flapping in the wind or even like fans moving, it's worth it sometimes just to think about, okay, how is the air moving over here, and maybe how is some of that motion being created by differentials or differences in air pressure?
Like in that scene in American Beauty where that dude was videotaping that bag flowing around.
Yeah, absolutely.
Oh, yeah,
right?
yeah.
Yeah, and certainly, I mean, that's a sort of a silly scene from a movie, but it is sort of a thing where this guy is just sort of amazed by the way that air can move a bag. And I think, if you can kind of get to that state of looking at something simple and being like, oh, that really is, there's a lot going on there. And as scientists, I think science gets this bad rap as a technical school subject when it's really, it's a way of looking at the world and trying to figure out how things work. And there's lots of different ways to do that. There are people that do it very technically, and there are people that do it very artistically, I think. And there's a way to look at it, as I'm just going to figure out all the beautiful, simple things about the world and how they work and how I can understand them for myself. So, going a little existential there on Homework Hotline Science Lab. But I think we'll wrap it up there for today. So thank you guys so much for joining us. We will be back in the Homework Hotline studio in just a minute.
There's times when you wander and ponder all the labels you've received.
Believe me, I've got a few. Never mind from when, why, or how.
'Cause now, everything's different. I found the perfect place.
A space where the labels fade and I'm accepted and supported.
Check what the news reported. Emily Griffith helps all who wish to learn.
Turn towards your future while you finish the basics on your time.
Prime opportunity in this mature environment.
The only requirement is motivation and thirst for success.
Invest in your passions. There's no limit to how far you'll go.
And know that you'll have something in common with everyone here.
We all chose empowerment over standing still in fear.
Welcome back. Hopefully you enjoyed our science demo. I definitely learned a little bit about air pressure that I did not know before. It makes me feel a little bit better about flying in an airplane, I think.
Yeah, I think it does kind of when you know that it's not just magic.
Not just magic.
That like allows it to lift up. And when I was younger, I used to think that it was, I guess that it was just so fast that would like allow it to go into the air. But it seemed a little like wishy-washy to me, like how. And then something of the motor or the propeller is like, or like the propeller on propeller planes is like pushing all this air behind it, and that's causing it to go forward. But it's much more complex than that. Really, what propeller planes are doing is forcing air over the wings to create that really
As
fast,
fast as we can.
and then you get that lift.
Oh gosh,
That's
it
really
makes so
cool.
much sense.
So then with jet airplanes, it's just it's just the extreme force of the air going.
Exactly.
Oh, okay.
Exactly. You can use those jets to sort of create differences in air pressure.
Okay.
And really control. It's amazing what they can do with this. You know?
Science.
Really.
Amazing.
Anyway.
All right, well, let's go get some more questions answered. Maybe more science
Yeah,
questions.
come on.
All right.
Do it.
Great.
Oh.
But wait, before we do that, actually, trivia question.
Yes. Let's
Give our viewers a chance.
let's read. We have what is the hardest substance in the human body? That's the trivia question right now.
So if you have an answer to that, you do still have some time to give us a call and prizes.
Yes, indeed. And, well, you know, I've got my eye on this little question over here. This is kind of interesting. This is, it says, we learned in school about parts of the human eye. I am still unclear on the rods and cones work in the retina to sense light. What is the difference between the rods and cones, and how do they help us see?
Mm-hmm. Yeah, so rods and cones are really fascinating. Rods and cones are structures that are collectively referred to as photoreceptors. Photo is the sort of sciencey prefix for light. I don't know if that's a Greek or a Latin prefix, but in any case, photo means light, and then receptor obviously means something that receives information or a signal. So a photoreceptor is going to be a structure, a cell-based structure that reacts when it is hit by light. Cones and rods work in different ways and sort of give sort of a multi-dimensionality to the way that we're able to see. So rods have the ability to perceive lightness and darkness. So as light hits them, they're able to perceive how intense that light is. And so they're able to see, again, brightness and darkness, and then also movement. And so in your eye, you're going to have a mixture of rods and cones embedded together. I think I've even got a picture here that'll sort of show us. Yeah, if we could jump to my screen really quick. I just have a scanning electron microscope picture of an eyeball way up close. And you can see right here we have rods are these smaller structures and cones are these larger structures here, and they're sort of embedded together. And again, the rods are receiving light in some capacity, and they're able to tell how bright that light is, how intense it is, and sort of motion from that direction of light. Okay, so then cones are maybe the thing that we think about a little bit more, because cones are what allow us to see color. And color is something that I think really is important to us as humans. So cones are going to be able to sense differences in wavelengths of light. So let me jump to another picture here. So we may be tempted to think of light and color as different things. And we may even be tempted to think of light and color, even if we think of them as the same thing, we may say, okay, well, sure, but radio waves are a totally different thing, and X-rays are a totally different thing. But actually, all of these things are just sort of focused beams of energy. And what we see as color is what is called the visible spectrum of light. So what I have here in this image is really a pretty cool graph that shows the wavelength, and sort of the wavelength and frequency of a beam of energy. And we can see that these very tight wavelengths up at the top are a type of energy called gamma rays. As they widen a bit, you get X-rays. Here in the 100 nanometers to 1 micrometer range, we end up with the visible spectrum of light. And then we have microwaves and radio waves. And the point I'm trying to make here is that all these things are the same in the sense that they're all energy. The differences between them is simply their wavelength, and we can see a small spectrum of this energy, and we call that visible light. And it's all the colors that we're able to see: Roy Jabib, right? Red, orange, yellow, green, blue, and indigo and violet. Indigo is not included here, but that's fine. And we might be tempted to say, well, look, those are all the colors that exist. Our cones in our eyes, we have 3 types of cones. And we refer to them as I think, small, medium, and large cones, related to how small or large the wavelength they can perceive is. What this ultimately lets us do is it lets us perceive red light, blue light, and green light. And it's the combination of those kinds of those three colors that allow us to see all of the colors that we're able to see, which is kind of a cool thing. But even cooler is to think of that there are a lot of creatures out there that have different cone setups than we do. And to make this point, I'm going to reference I'm going to show a little bit from a web comic called The Oatmeal, which is an amazingly cool comic. And this guy who runs this does a really good job of explaining sciencey concepts. But really quickly, we'll just look at, here's this picture of dogs and says, okay, so dogs have two types of color receptive cones, green and blue. And so that lets dogs see blue, green, and a little bit of yellow, because you can mix green and blue light to get yellow. Humans have three types of color receptive cones. We have green, blue, and red, as I already mentioned. And that additional red cone allows us to see all of the colors that we see just through the mixing of light, right? And so you might think, oh, we're pretty great. We're pretty evolved. We can see so many more colors that dogs can't. But did you know that butterflies have 5 types of color receptive cones? And so there are 2 colors that I can't even describe to you because there's no real way for us to know what those are like. They're really just different wavelengths of that energy. Again, over here that we were talking about, there's a wider range of energy that these butterflies can see because they have 2 additional cones. But the really mind-blowing thing, and I'll wrap it up here after this, the really mind-blowing thing is that there are creatures that have even more than 5 cones. And the most interesting one, and one that gets referenced most often, is this thing called the mantis shrimp. And this comic is about the mantis shrimp. Totally check it out. This guy does really great work. But as he points out, they have not 2, not 3, not 5, but 16 color receptive cones. And so an ability to see an incredible range. And so what that would mean is that this creature could see could see heat energy. So imagine, I can see Jeff across the studio from me here. If I could see like a mantis shrimp, I could actually see the heat off of Jeff's body as if it was color. And this is what we see when you see people that use infrared goggles, right? Infrared goggles are goggles that allow you to see infra lower than red wavelength. So we can't actually see this stuff with our normal eyes, but these goggles pick it up and turn it into something that we can see. And so infrared goggles allow you to see things like heat emitted from a body. But certain animals like the mantis shrimp, butterflies, and surely many others out there are able to actually see heat as a literal part of the world that they live in. So I think that's pretty cool. But anyways, back to the original question. Rods let you perceive intensity of light and movement, and cones let you perceive color. And we have 3 kinds of cones as humans.
That is so
That is
cool.
really cool,
Yeah, it's super interesting, right? There's this really
trying to
great
picture that. I mean, but we can't.
Well, there's all these like funny references to it. Like there's this show that I watch where this religious character talks about blurple, the color blurple, which is a secret color that God keeps secret for a reason. And there's a book series called the Discworld series, and the first installment in the Discworld series is called The Color of Magic. And in the book, there's this extra color that is the color of magic that certain people can see. And it's neat because the author tackles this idea of a color that some people can see and others can't. And it's a fantasy book that has nothing really to do with science. But it's interesting, and I think that philosophical question of like, what does a color look like that we can't see, right? Like you would try to describe it using colors that you already have. Oh, it's a mixture of orange and purple, but it doesn't work that way. It's
out of the range. It's outside of the range.
Well, so we call infrared that stuff that has a longer wavelength than red, because we can't think of anything longer wavelength than red. Red is our stopping point, but infrared light doesn't look red. It must look like something we can't perceive. Ultraviolet light is higher than violet. It has a shorter wavelength than violet. But we don't really know what it looks like. Violet's just as far as we can go, so we just call everything beyond that ultraviolet.
You know, I think it's interesting is how do they figure out, and I think I just realized it as I was listening to you talk, like how do you figure out that a butterfly can see more colors because you can't see what a butterfly sees? Or how can you figure out that a dog can't see color?
Positively.
But I guess if they know that our eyes process color through these rods,
exactly,
and they know that a butterfly has more, then they have to be able to see more, or a dog has to be able to see less.
Right. I mean, we would literally, so we can look at different cone structures in human eyes, and we can compare those to cone structures in other creatures' eyes.
And that's why they didn't show any of the colors on those little circles when they were talking about.
Exactly.
Because they don't know what
we don't know what that actually would look like.
The other 2 colors are white.
And what's really crazy is that it's like those are additional cones. So those are additional like primary colors, let's say. Those are additional building blocks of colors. If we can see everything we can see with 3 wavelength perceiving rods, or cones, excuse me.
Oh my gosh.
Imagine, so it's like it's a multiplication question in a sense, or it's like all of these. It's an exponential question. All of these colors stack on top of each other. So I can't even imagine. I mean, I have a feeling like I can see so many colors. Like it's infinite, the range of colors for me. So what must it be like for a mantis shrimp?
So interesting. All right. Well, I think it's time to do the trivia question and the answer. Yeah,
cool.
Get our answer.
All right.
Let's do that.
All right, well, let's get to the trivia question. The trivia question was, what is the hardest substance in the human body? And the answer to that is, it is tooth enamel. That's right, tooth enamel. And tooth enamel is interesting because it's a part of the tooth, it's visible when you open your mouth. So when you open your mouth and you see the white teeth, that is a tooth enamel. It's the hardest substance in the human body, and it's even harder than a diamond. So that's interesting. The human bite can exert up to 200 pounds of pressure on its back teeth. And enamel's job is to protect your teeth. It provides the insulation for your tooth so you don't feel discomfort while you're eating and something that's hot or cold. The nerves in your teeth are sensitive to temperature. So if you have some pain in your teeth while eating hot or cold foods, this could be a sign that your enamel is eroding. So be careful.
So it is even harder than your bones. I almost was going to say the hardest substance in your body is your bones.
Right.
But it's not.
Yeah, I've been called hard-headed, so I thought maybe it was like my skull was the hardest.
Nope.
Right.
Yeah.
It's your teeth. So enamel is pretty much made of calcium and phosphate. But the proteins that form them stretch these like mineral strands that are like around your teeth that are 1,000 times longer than bone, making the enamel more resilient. And then unlike a broken bone, it can be, your enamel can be repaired by your body. Once your tooth chips or breaks, a broken bone that can be repaired by your body. So our body can actually repair our bones whenever we break them. Like when you heal, we get them set, and then they kind of rebuild themselves. Once your tooth or chips breaks, it's done. It's done forever. So that's why we have our fake teeth there. But
Yeah.
I don't know. That's what I know pretty much about.
And I think enamel, that's the thing that people worry about when they talk about, it's too much sugar in my diet, or I'm drinking too many foods that are acidic and it's breaking down. You can do damage to the enamel, usually through chemical breakdown of some kind. Acid reacts really easily with enamel. So folks who drink soda, I actually drink a lot of soda water, and for years I thought I'm safe because there's no sugar. But it turns out that's not true.
Yeah, I
There's
was
carbonic acid, that's why it's fizzy, so I actually do have to be careful.
So even if you're drinking soda water that doesn't have any sugar on it, it's still hard on your teeth.
It's worse. It's worse with sugar because you have a combination of sugar, and also all soda contains another kind of acid. But I won't get into that right now.
So I've heard, though, if you want to preserve your teeth, obviously go to the dentist and stop drinking so much soda. But also drinking more dairy. So like, it's good for you. Cheese and dairy products. They're high in calcium and phosphate, so they can actually remineralize your enamel.
And I was going to say you can actually brush with mineral powders that are supposed to remineralize your teeth also.
Maybe if you have soda milk, it will just balance it out.
Oh, perfect. Carbonated milk.
Oh,
Definitely going to start a soda milk company. That's coming.
Not going to go there. But.
Have your soda, but strengthen your teeth too.
All right. Well, we do have to say goodbye. Thank you for joining us this week. We had such a great week this week on Homework Hotline. If you have any questions that you didn't get answered from your homework, feel free to send those in. We can always get to them next week. But that being said, enjoy your weekend, and we'll catch you later again next week from 4:30 to 5:30, Tuesday and Wednesday, and we'll see you then.